Hello, welcome to MA3D1. This video is about force on immersed bodies. This is treated in section 6.5 of the notes. Let's start with a brief recap. The first item we are going to use is the definition of potential flow, where the velocity is the gradient of a potential, and the second is Bernoulli equation, but for the case of potential flow, which is potentially unsteady. The topic of this video is as follows. We have a body of some shape, general shape, in 2 dimensions, which is immersed in a flow which is uniform far away and would be uniform in the absence of the body. Now, the body would modify the uniform flow to go around it to satisfy the no penetration condition in the case of potential flow. In reality, it will also impose a no slip condition, but we are going to ignore that condition because we do not have the ability to impose it in potential flow. So this flow will be given by a potential that will in complex form will look something like this: uz plus q minus I gamma over 2 pi log z plus a1 over z plus a2 over z squared. So that far away, when z becomes large, the velocity from all of these terms vanishes or decays to 0, and we are left with the uniform flow. So that is how this potential, you'll remember, was constructed. Now, for this, the flow represented by this potential, there is a corresponding pressure, and because we have not satisfied the no slip condition, we are going to take the case of an inviscid fluid. In which case, the stress tensor is simply given by minus P times the identity tensor. And then the force on any body is given by integral minus P n hat dA for the boundary of that body. So let me say this is omega and the boundary is delta omega. So in this video we are going to substitute the pressure we get from Bernoulli's for this potential into the expression for force and evaluate. We are going to break down the calculation really in 3 parts, but only 2 of them need some attention. The pressure coming from the constant will give you a force of 0, because a body which is acted upon by a constant pressure on all sides does not experience any force, so that doesn't need to be accounted for. Then there is the force of hydrostatic pressure, but we already worked this out. This is the first part, right? The contribution from hydrostatic pressure. You remember what the answer was? Or do you remember that we worked this out? Minus P n hat delta omega is minus the pressure term is rho gx n hat dA over delta omega, and this turned out by Archimedes' principle, which we derived by applying divergence theorem to this integral, was rho g times the volume of omega. So This is the Archimedes principle, and you get the force of buoyancy from this term. So we don't need to account for that term separately. The only two terms that we have not yet examined carefully is this one and that one. And we are going to start with the u squared term because that would be present in the case of a steady flow. It would also be present in the case of a time dependent and unsteady flow. But it so turns out that if you pretend that the flow was steady at that value, the force we get is so surprising that we don't need to worry about the fact that it is unsteady. So we are going to call this part the steady potential flow. But mathematically, we are going to say P is given by 1/2 rho magnitude of u squared. And then I'll call this Fs for the steady part equals delta omega minus 1/2 rho magnitude of u squared n hat dA. And in order to perform this integral, we will have to use a complex variables trick. To understand this neat little trick, I'm going to draw like a tiny portion of this segment here. Okay, so I have the body on one side, and then I have a flow that is everywhere tangent to the shape of the body, right? So this is one of the streamlines, for example, let's say. The tangent, which I'm going to draw in green, is along that direction, which is parallel to the local velocity, and the normal, which I'm going to draw in red, is in that direction. So that's n hat, and in green was the tangent. Okay. Now we know from complex potential flow theory that the velocity can be written in terms of the components of the velocity can be written in complex form as w prime of z. So this is what we are going to use, this and other complex manipulation techniques. So if you say that the tangent makes an angle theta with the x-axis at some location, then this velocity will be parallel to the tangent. So the velocity will have an argument of theta as well, written in complex form. But what I have written here is not the velocity but the complex conjugate of it. And therefore, I can write this as the magnitude of u times e to the minus I theta. Pay attention to the minus there because I have the complex conjugate. All right. This is purely real. So the complex nature of this expression comes only from the e to the minus I theta. I put the minus I because I have the complex conjugate. All right. And I use this to solve for the magnitude of u in terms of w prime of z e to the I theta. And from that I'm going to find the magnitude of velocity squared w prime of z squared e to the 2I theta. So that's that term done. The density rho is a constant, so that will just come out of the integral. The next thing I want to tackle is the unit normal. But before I tackle the unit normal, I'm going to now write this whole expression in complex form as fx minus I fy. Note, I've written the complex conjugate of the force, and this is going to turn out to be critical. Because I have the complex conjugate of the force, I should write this as some contour integral I don't know, I have the negative there, it should be positive. Times n hat. N hat is what gave this expression its vector character, and now I have broken up into components and then I've combined it in that expression. So really what I want here for n hat for the direction is the complex conjugate of this normal. The tangent was e to the I theta, so the normal is minus I times e to the I theta. I rotate the tangent clockwise 90 degrees, that's equivalent to multiplying by minus I, and I want its complex conjugate here, so I get I e to the minus I theta times the arc length element. I will assume unit width out of the plane of the paper, so the area element will become the arc length element. The arc length element here, so let's say this is ds. Now we want to write ds also in terms of the complex element dz, and that relationship is that dz is ds e to the I theta, again on terms of this angle theta. So I can write ds as dz e to the minus I theta, and dz e to the minus I theta. Now you'll see what happens when I plug this in there. I get a complex contour integral over this contour C, which is the boundary of the body, 1/2 rho w prime of z squared e to the 2I theta e to the minus I theta, and then another factor of e to the minus I theta. There is a factor of I and dz, so I will write the I over here and dz, and all these terms, they all multiply to 1, e to the 2I theta times e to the minus I theta twice, and we are left with a purely complex integral of that form. Now if you have done complex integrals on closed contour C, because the body will have a closed shape, you will know that the answer depends on, like, the answer will be based on Cauchy's theorem, and will depend on whether there are any singularities of this function of the integrand inside. So let's find. We already have, I have written down w of z here. So let's find w prime of z. W prime of z is u plus, now actually q minus I omega over 2 pi z. Here we can take without loss of generality that q is 0 because of mass conservation. Because if there is a source inside the body, then that body is somehow releasing mass into the fluid, and that violates our assumption that we just have a passive body inside the fluid with immersed in a free stream. And so therefore, to conserve mass, we take the source term to be 0, minus a1 over z squared minus 2a2 over z cubed, and so on. And if I square this, I get w prime of z is u I gamma over pi z. Wait a second, let me write it this way. Yeah, let me write it this way. Minus I u gamma over pi z plus u squared plus minus gamma squared over 4 pi squared z squared plus higher powers of 1 over z. And now if you do this, if you take this w prime of z squared and substitute it in this expression here, what you find is that fx minus I fy why do I have a extra I? Let me investigate. Everything is all right. I think I know why I thought there was an extra I, but there isn't. So we now substitute it in there and we get I rho over 2 times 2 pi I from Cauchy's residue theorem times minus I u gamma over pi, which all simplifies to, you will see I squared cancels the minus, 2 pi cancels the 2 pi, and I'm left with I rho u gamma. Yes, so that is fx minus I fy, and that implies that the force in the x direction on the body is 0, the force in the y direction on the body is minus rho u gamma. These are the two results that we have derived so far. Now let's start with the second one. Okay, and to tell you the truth, you have seen this second result before. This was one of the previous example sheets where we had a flow given by the linear superposition of a uniform flow and a point dipole. This was example sheet 3, I think, where you had to use the integral conservation law to find the force exerted on a fictitious circle of some radius r. And you find that force and you find the answer is always rho u gamma irrespective of your radius r, and from that you deduce that this was the flow because of a point force in the vertical direction acting on a fluid which was flowing uniformly otherwise with speed u. Example sheet 3. I think. But this result just generalizes our consideration from example sheet 3. Like there we did it using integral conservation law. Here we have some arbitrary streamline that represents our body, but I could have used any closed streamline, right? And if I had not used a closed streamline, and if I had used some conservation law, I would still have gotten the same answer. So the answer is independent of the method because it is rooted in the physical reality, and it is given by this expression. So this result is called the Kuta-Zhukovsky relationship theorem. It states that the force on a body in potential flow is a result, it is in the direction perpendicular to the flow. In 2 dimensions if the flow is in one direction, there is only one perpendicular direction remaining, and its magnitude is given by these three terms: rho, u, gamma. In the next lecture, we are going to see how this result is used to calculate the lift on airplane wings. But for this video, I thought it would be interesting to put some popular science in perspective. All right. So back when I was first preparing this lecture, I came across this video, which I think remains relevant and interesting still today. So let's watch this video. I will narrate because I don't think the audio gets recorded. The audio from the YouTube video gets recorded. So this is a giant dam, very tall, several, I think hundreds of meters, more than 100 meters. And then what these guys are going to do is to let this basketball fall first by itself and then with a spin, and you will see what happens. If you haven't already seen this video has got 8 million views, so it's very likely that you've seen this video. So when you drop it without spinning, it just falls down like a rock. There are some aerodynamic forces, and you see the ball does not fall straight vertically downwards. But now, watch what happens when the ball is dropped with a little bit of a spin. So as you can see, this is a systematic effect. The spin is what caused the basketball to really take off, right? So I thought it would be a good idea to use this calculation that we have made so far to explain why the basketball behaves in this way. This is an effect called the Magnus Effect. And the idea is that when you have an object like a basketball, let's make a two-dimensional model of it. Then as it is falling down, there is a uniform flow U incident on it. And because of its spin, the potential flow that is set up around the ball will have a point vortex gamma that is proportional to the rotation rate of the ball. So it's only when you have both of these together that there is a force on the ball, and let's see which direction the force will be. And you can obviously use the maths that we have derived so far to get the force, but also to understand the physical reason why there is a force. So now, without the spin, the streamlines around a circle are perfectly symmetric, right? Because there is nothing breaking the symmetry on one side or the other. But with the spin, you superimpose this sort of a point vortex, and if the ball is spinning along the arrow that I have shown in this picture, so that means the contribution to this fluid speed from the spinning ball on one side will be in that direction, on the other side will be in that direction. So you'll see the fluid is flowing this way because of the free stream as well. So here the speed will be higher because superposition would make the two speeds add up. Here the speed would be lower because the velocities from the two terms are in opposite direction. We know from Bernoulli's equation that where the speed is lower, the pressure is higher. And where the speed is higher, the pressure is lower. And the net effect of all this is that there is a net force on the basketball which pushes it towards the low pressure region. And now go back and watch this video. Here is the link. You can basically search basketball dam and watch the first 2 or 3 videos that come up. They're very interesting to watch from a fluid mechanics perspective anyway. So pay attention to which way the spin is and which way which way the spin is and which way our simple model predicts the force, and whether you do indeed get the force in that direction. All right. So that's the Magnus effect. It's not only so, and this is really the appeal of potential flow. You see, it was such a simple model, and with such elegance you can derive such simple equations, quantitative, and also you can make qualitative sense of observations like lift on a basketball because of the Magnus effect. Right? And the next lecture we are going to see the lift on an airfoil. And this is the appeal of using potential flow, at least in situations where inertia dominates, the Reynolds number is high, so you can just neglect the viscosity. But the problem is on this side. How can you have no drag on the basketball? How can you have no drag on an object immersed in the flow? No drag. This is called Thalambear Paradox. And it flies in the face of common experience. And because of this, you have to ask the question, was potential flow theory really accurate? Was it really correct, or is it really correct? Now, what we know today, which we did not know about 120 years ago, was that no matter how small the coefficient of viscosity is, we cannot neglect it everywhere. And we are going to see this in much more detail in the next chapter, which I think will be the last chapter we will consider in this module, boundary layers. And we'll arrive at some sort of a resolution to, well, is potential flow, what is the role of potential flow in a general fluid dynamics theory? It works so well for some things, it doesn't work so well for others. In fact, it just falls on its face for other things. So how should we put together a more general theory of fluid flow? When we learn about boundary layers, we'll have a better picture for doing that. So this is the force on an immersed body from the steady potential part. We are left with one more term which comes from this unsteady part, and now we are going to see what to do about that. So let's look at the force because of the unsteady. And instead of just calling it force, this actually leads to a phenomenological explanation for the force in terms of an added mass. Added mass because of unsteady term. Right, here we are going to calculate Fu is rho d phi dt minus sign, the plus sign dA, and there's the omega. The same sort of consideration, so is an n hat, yeah, that's why I left the space. And instead of doing it for a general body, which can be done without too much trouble, to illustrate the basic principle, we are going to take the flow around a cylinder. W of z is u z plus a squared over z, flow around a circle. And in this, from this, we find the velocity potential phi, which is the real part of w, and in polar coordinates this is going to be u r cosine theta plus a squared over r cosine theta. So I'll take the cosine theta out, and because this is a flow around a circle, let me now draw a circle to the best of my ability, and angle theta, this is a circle of radius a, and angle theta is drawn there. On the surface of the circle, the force, because of the unsteady term, rho del phi del t at r equals a, n hat is just r hat, which is cosine theta ex hat plus sine theta ey hat, and dA is just a d theta times the width perpendicular to the plane of the paper, which we will take to be 1. But here we will need the d phi dt term, which if I differentiate this expression for phi, I get the d phi dt from the du dt at r equals a, so our force is from 0 to 2 pi rho du dt a cosine theta times 2 times cosine theta ex hat plus sine theta ey hat times another a d theta. You do the integral and you realize that the integral of cosine squared theta from 0 to 2 pi will be something non-zero. In fact, it will be pi, and the integral of cosine theta times sine theta will be 0. One is odd, the other is even, blah blah blah. We can do these integrals without too much trouble, and you get 2 pi a squared times rho times du dt ex hat. Yeah. And it so turned out, because of symmetry, we only got a force in the x direction. For a body of general shape, you can get both a force along the x direction and a force along the y direction. There is no need that the force be along the direction of the flow. Right? But what is the origin of this force is that it is proportional to the acceleration of the fluid. In order to understand this, you have to move back into the reference frame of the faraway fluid. Now, we took the faraway fluid to flow uniformly. So when you move into its reference frame, the faraway fluid is stationary and the cylinder and this circle is moving back, right? Oh. Yeah. The circle is moving back. And if u is a function of t, that means the circle is moving back with a time-dependent speed. Now, if the circle were made of a solid body, and if you ignore the fluid, in order to move the circle, in order to accelerate the circle, you have to exert a force. In the presence of the fluid, not only do you have to accelerate the circle, but you have to move the fluid out of the way. And if the speed of the circle starts increasing, then the speed of the fluid around it must also increase proportionally. That's what this term represents. That's why the acceleration of the circle starts mattering. And you multiply the acceleration of the circle with the mass of a certain amount of fluid. That must be pushed out of the way. or that must also be accelerated along with the circle. And this mass is what is called as added mass. It is as if, because you are not only accelerating the circle, you are also accelerating the fluid around the circle. It is as if the fluid adds additional mass to the circle. You can check dimensionally density times area times unit width perpendicular to the plane of the paper gives you a mass. So this is the origin of the added mass term. To summarize, there are three contributions to the force exerted by the fluid on a body. The first comes from buoyancy, the second from the steady term in the Bernoulli equation, which leads to Kuta, Zhukovsky lift, and the Thalambear paradox for drag, and it leads to the added mass term for unsteady situations. Now, even if when the flow is unsteady, the steady term will still contribute. It will contribute a force that is given by the Kuta-Zhukovsky expression, but the terms in that expression will be functions of time. In addition to that, we get the added mass. Okay. And that's the summary of this video. This brings me to the conclusion of this video. I will see you in the next video or in the next live session. Thank you for your attention.